Hi, welcome to another video. You'll be pleased this is the last in the series for this Epson S1D13517. I finally got the alpha blender working. Before I show you a sample of the alpha blending, my brother said he'd like to see some of the code. I'll turn to the computer and run through some code. So if you've ever looked at the datasheet for the S1D13517, you'll see this near the beginning. If you want more from your display other than showing regular pictures, you need something like this Epson chip. But more importantly, and which is why I've wanted this chip for years, you can blend two pictures together. In my previous video I showed you I had 13 pictures. In the first 13 buffers of this memory, the memory has 16 buffers. You can take any two images from anywhere in the memory, blend them together and output them to any buffer you like. That's what all these lines are for. So unlike a previous project which I've showed on YouTube, this Epson chip controls the SRAM, and that's an awful lot of work off of your hands. It does all the alpha blending and sends a little signal from an interrupt pin that lets you know when it's finished. So a quick look at the memory. This is the memory chip I've got here, 16 megabytes, 128 megabits, 4 banks of memory. It's selected with DQML and DQMH. That's memory high, memory low. But there's just 2 pins on that. How do you select 4 banks of memory? I've got the truth table down there. So it's 16 megabytes of SD RAM, D for dynamic, the RAM random access memory. So unlike flash memory or an EEPROM, DRAM is volatile and will lose its contents if power is off. As I mentioned before, my screen is WVGA, wider video graphics array, so it's not something like 640 by 480, it's 800 times 480. 800 pixels wide times 480 pixels tall, that's 384,000 pixels. Each picture stored in my SD card has 2 bytes per pixel. And I've got a little note there for the noobs. So this is byte 0 and byte 1. And as I've mentioned before, 5 bits of red, 6 bits of green, 5 bits of blue. If they're all 0, you'll have a black screen. If just the reds are on, you'll have red. If just the greens are on, you'll have green. If all the blues are on, you'll have blue. If they're all on, you'll have white. If you mix the green and red, you'll get yellow, etc., etc. So byte 0, byte 1. 76,000 bytes for one 16-bit colour bitmap, plus 72 bytes of info called a header. The 72 bytes contain information, so your phone, laptop or PC and my program looks at the header to see how wide and tall the picture is, how many bytes, and using that information it's able to display it. Since my 16-bit pictures, 2 bytes per pixel, here's a look at how I get the data from the SD card. It's a simple for loop, but the important bit is, so PMD in is actually the data out to the Epson chip. So data buffer X could be data buffer 1, ORed with, so joined with data buffer X plus 1. This X plus 1 is shifted left 8 places. So it's making the least significant byte more significant by moving it left. Got a note here, PMD in is actually the 16 data lines out, but the PIC32 ECM, which is the microcontroller I have today, does not have PDM out register. The EFH144 does. You can see it looks at the 2 bytes, joins them with the OR, that's putting the least significant byte first. And that is what the Epson chip actually expects. So once it's dealt with those 2 bytes, you can see X equals X plus 2. I've got a note here. I could have written X plus equals 2, but if you're a novice, that doesn't make sense. X equals X plus 2 does make sense. So, why complicate things? So my 800 by 480 screen, 384,000 pixels, multiplied by 2 bytes per pixel, 768,000 bytes for one image. The Epson S1D13517 converts the 16-bit red, green, blue into 24 bits per pixel. So 8 for red, 8 for green, 8 for blue. So that's 1 whole byte per colour. So since the Epson chip converts it to 24-bit, that's 800 times 480 times 3 bytes per pixel. That's 1,152,000 bytes per picture. So why am I talking about memory? The Seiko Epson Corporation datasheet tells you to specify how many bytes in memory each buffer should contain. But then they say in 16K amounts. So what's 16K? I've got a note here for the novice. So you've got 1 byte, 8 bytes, 16, 32, 64, 128. You can see each number up to the right is doubling the previous number. 256, 512, 1024, that's 1K. 2048, 4096, 8192, 16384, that's 16K. That number's important. So to allocate the memory size, their example quotes hexadecimal 40. Hexadecimal 40, if you convert it with Windows calculator, is decimal 64. See, I've got a note here. 64 times 16K equals 1,048,576 bytes per buffer. But up here you can see we need 1,152,000. So this number isn't big enough. So for my screen I need 1,152,000 minimum per buffer. So 1,152,000 divided by 16K equals 70.3125. You can't have non-whole numbers for your memory size. It has to be full integers. So I've got a note here, so let's use 71 decimal. 71 times 16,384, 16K, equals 1,163,264 bytes per buffer. And it works because that's what my program is running on. So why am I going on about buffer size? To get the alpha blending working, you need to know your exact buffer size. The blending relies on where are you taking your pictures from, which buffer, and where are you sending them to once they're blended. So I've got a note here, so this 1,163,264 bytes, that does not look like a number you would see in code. So you must convert it to hexadecimal using Windows calculator, because that's what programmers do. Here's a capture of my Windows calculator. So there's a decimal number, and it converts it to hexadecimal 11C000. 11C000. No one can understand this, but it looks great. I had defined the buffers like this, but once you define something, you can't alter it. You'd have to have a pointer to point towards it. So I scrubbed that idea and went to this idea. 15 buffers, all numbered 0 to 14, so that's 15, and there are the addresses. Easy. There's a closer look in case you've got a mobile phone. So having the buffers like this, I can manipulate them. Having them as defined, I can't. So with the standard instructions on the data sheet, they say you take 2 images, picture 1 and picture 2. The alpha blending blends picture 1 or part of it with picture 2. Now in this picture here, picture 2 is the lion, and you can see it stands out. Picture 1 is being blended in the background, and you can increase how much of that picture you want to see or decrease it. But the lion is always there. And even though this is the first time I've had alpha blending, I thought it was pretty naff. So picture 1, any buffer, in this case it's a city skyline. So picture 2, lion, it can be from any buffer, but in this case it's whatever buffer that lion was in. So you keep adjusting the blend ratio of picture 1, the skyline in the background, until it either disappears or comes into view. And when it comes into view, it will overwrite the lion. As I just said, it was okay, better than I'd seen or in before, but picture 2 always flashed up full, and the second picture, picture 1, would fade in or out. I took control of the buffers and their corresponding addresses in memory. I chose to add a random function for both buffers. Picture 1 would fade in or out, and another random picture, picture 2, would appear in full colour. But sometimes, if a picture had faded out and my random number for picture 2 happened to pick that faded out picture, picture 2 would fade in and then picture 1 would fade in. It looked pretty good. So both pictures fading in and out, not just one appearing and a second picture fading in. So I then spent a few hours getting both pictures to fade in and out. So here's some simple instructions. The datasheet tells you how to do it, doesn't go into specifics, but having it laid out like this just makes it easier, or I think it does. So you set the picture sizes for your pictures. They've all got to be the same size for blending. You set how many pictures to blend, 1 or 2, and how much you want picture 1 blended with picture 2. You write the data to the Epson, so 2 image ORed with the alpha value. These are actually numbers, and I chose to put in words, and I could just change the words. And this alpha value is a variable, so I can change it in a for loop. So this 2 image can be changed to 1 image, and it simply blends in one picture at a time. 1 image or 2, ORed with the alpha value. So step 2, set the input memory address for picture 1. That's the buffer number in the SD RAM. Write data Epson memory address 1, memory address 1 shifted 8, memory address 1 shifted 16. So I've got an example and note. So buffer 1, for example, 11C000. The address registers must have been done in my brother's country, Australia. And here's the number turned on its side. OX11C000. You can see it's upside down. The least significant byte comes first, then the most significant byte comes last. That's little endian. So once you've set the input memory address for picture 1, you set the input memory address for picture 2. So memory address 2 shifted 8, memory address 2 shifted 16. Then you set the output address. So since I've got 13 pictures, buffer 14 was empty, I chose to set the output address to buffer 14, and the address is defined earlier. Here. So one noteworthy point, this register then automatically increments, and the next register, if you don't specify one, is the register for this memory address 1, for the input. Then that register, then that register, then this, then this, then this, then the output registers. So if you do them in that order, there are loads of commands you don't have to write. These are data. The command would be which register are you sending what data. So you can delete a load of commands by doing it in this order, which is actually described in the datasheet. Or they describe it in the datasheet, but not why it's done in that order. But if you look at the commands, you'll see they follow sequentially. So you can delete the commands, because as I've said before, this Epson chip auto increments the registers. Even some of the interrupts follow from this last data. So you set the interrupts, etc., so you know when the blend is done. So you keep on increasing the alpha value. And I've got a little if statement. If the value goes over 32, you set the value to 0 and it starts again. Now, even though the alpha value, if I bring up a calculator, can't really make this bigger. So the alpha value is bit 54321 You can see that's decimal 63. But if you set that value to over 32, you get funny pictures on the screen. The actual image turns white. So I don't know why there's 5 values. In fact, let me just check. So that's 63. The biggest value you can put in is 32. So if I type in 32, oh, that's why. You need this bit 5 here. So 765. you need that part of the register to get 32. But however, if you fill them all with ones, your image will go all white. So if the alpha value goes over 32, it sets it to 0. So once it's adjusted the alpha value, it goes to step 1 to adjust the alpha value to increase it. Step 1, back up here. Once it's adjusted the alpha value, the memory address for picture 2 is altered, and the buffer is now a random buffer. So after the memory address for picture 2 has been set to a random buffer, I change the random number after it. So random equals rand %13. That means it counts up to 13 and no more, because I've got 13 pictures, 13 registers, using the 14th buffer to show the blended pictures. So this generates a random number. Then I change the memory address for picture 1. But putting this before the random change, once the image has been changed, and this is here, not down here, both images blend in. If you move this bit down here, the picture appears and picture 1 blends in. Putting this up the top makes it actually work. So I've got a note here: the location of the memory address 2 and the random buffer is important. If you move it somewhere else, it won't look as good. So there's a million things I haven't covered. Once you get to grips with the memory, everything's straightforward. So now you know how to make a difficult system easy to understand. Well, here we are. So there's only 32 steps, remember? Now it's random, so sometimes the pictures are repeated, sometimes it doesn't change because it stays on the same number. I think this is impressive. That's a redback in my brother's bucket in Australia. Oh, and he's back. Or she. She'll kill you in half an hour without anti-venom. So this isn't the first video on YouTube demonstrating alpha blending. This certainly isn't the first one demonstrating alpha blending on an Epson chip, because Epson Corporation have got their own videos. But there's no talking on it, no code, the comments are turned off. I would have loved to get some sample code just to put me in the ballpark, just so I know what I'm doing. Hopefully, if you're going to use an Epson controller in the future, this file or this video will help you, and a C file will certainly help you because it's all there. I'll make the C file available, I'll put it on GitHub and put a link in the show more. If you want to donate money for a coffee for the weeks it has taken me to get this chip up and running, including the alpha blending, there's also a link in the show more. I'll leave you with this alpha blend running in the background for a minute or so, just so you see all the pictures. Not to this red back again. Go away. Yeah, so thanks to my brother for the picture of that red back. I'd like to say I'm pleased I don't live in Australia, but it's certainly warmer there than it is here in the UK at the moment. If you've got any comments, leave them below. If you've got any questions, leave the questions below. The C file is below, so you don't have to ask for that. Thanks for watching.